Hi there, and welcome back. What we're going to do is use aspects of f, the derivative of f, and the second derivative of f, all the properties with concavity, increasing and decreasing, domain, to try to sketch the graph of a function. And the function we're going to look at right here is f of x equals x minus 6 times the square root of x minus 1. So one of the most important aspects of a function is its domain. What values of x are going to return values, real values. And notice we have a square root here. So the domain is all the values of x, the set of all values of x, such that the square root is defined. So that right here is going to be the interval 1 to infinity. Close bracket on 1, because x can equal 1, okay? And there are no asymptotes to speak of here, so there's nothing going to happen with the asymptotes there. Now, ordinarily, we would also talk about intercepts. There is no y-intercept because x equals 0 is not in the domain of the function, and it's not very convenient to find the x-intercepts. We could set that equal to 0 and try to solve. It does get a little bit complicated, so we're just going to hold off on the intercepts until we actually get the graph of the function. We can approximate them. Okay, so as far as critical numbers go, now remember that comes from the first derivative, so we need to find the first derivative, and I'm going to rewrite the function f first. To the 1/2 power, because that is more convenient to take a derivative with. So this means that the first derivative, f prime, is 1 minus 6 times 1/2 x minus 1 to the negative 1/2, and then the derivative of the inside is 1. So I'm not going to write that down necessarily here, but we have 1 minus 3 times x minus 1 to the negative 1/2. Okay, so I'm going to save this for later because I know for sure that we're going to be taking another derivative and we're going to want the power version there with the negative 1/2 power. So thinking about critical numbers, usually we would set this equal to 0 and undefined. I'm going to rewrite the derivative in a more friendly form. Now remember, negative 1/2 power is 1/2 power in the denominator. And remember that 1/2 power really means the square root. So this is 1 minus 3 over square root x minus 1. Clearly, this is undefined when x equals 1. It is the endpoint of the domain, so it is something that we do need to consider in our number line, but we're not going to be able to substitute it because it's undefined. But it is also the endpoint of the domain, so there's nothing on the other side of it. And we do also know, so I'm just going to write here undefined when x equals 1. The other critical numbers can come from when the first derivative is equal to 0. So what I'm going to do is add the square root expression to both sides. Multiply both sides by the square root. Square both sides. So basically just that. Okay, and then add 1 to both sides, and it looks like a critical number is 10. So x equals 1, endpoint, x equals 10, something could be happening there. So remember what we do, we make our sign graph for f prime, and x equals 1 is on the extreme left of that number line, because we can't go to the left of 1. And we have 10 as our critical number. I should label that with a line, not an X. So now what we're going to do is test values to the left and to the right of 10 to see what this derivative is doing. Is our function going to change from increasing to decreasing? Are we going to get an extrema? Or are we just going to get a point where the tangent line is horizontal and then just keeps going in the same direction? So looking at our derivative again, f prime of x is 1 minus 3 over square root x minus 1. So I'm going to pick values of x so that when I subtract 1, I get a nice square root. So I notice that when I pick x equals 5, I end up with the square root of 4. So I'm going to pick 5. And I'm also going to pick, well, see, if I want the number underneath the square root to be, say, 16, I want to plug in x equals 17 to make a nice square root. So f prime of 5 is 1 minus 3 over square root of 4, which is 1 minus 3 halves, which is negative 0.5. So that means that our function is decreasing on that interval. And then at 17, we have 1 minus 3 over square root of 16, which is 1 minus 3/4, which is 0.25, which means we're increasing. Positive derivative means increasing, negative derivative means decreasing. So that means that this function is increasing on the interval 10 to infinity, and it's decreasing on the interval 1 to 10. So I'm not including 1 in the decreasing interval because it is an endpoint. Open intervals are what we use for increasing and decreasing. There is no local max because we're not going from increasing to decreasing. And it looks like we have a local min at 10. I was going to write f of 10. We'll figure out the value of that function later on when we look at the graph. So there we have all of our information from the first derivative. Now remember, second derivative tells us about concavity. So I'm just going to separate this out here. And let's see what we have here. So f prime at the very top of the screen there, I'll write it down again. F prime of x is 1 minus 3 times x minus 1 to the negative half. So that means that f double prime is, okay, so the derivative of 1 is 0 minus 3 times negative 1/2 x minus 1 to the negative 3/2. Now, if we simplify that a bit, we get 3/2 times x minus 1 to the 3/2, which is 3 over 2 x minus 1 to the 3/2. Now remember, the domain of the original function is x greater than or equal to 1. X equals 1 clearly makes this second derivative undefined, so we really only have one interval of interest here, and that is when x is greater than 1. So I'm going to draw my number line for my sine graph, and this is x equals 1 right here at the very end. I can't go before that. And the numerator is never 0, which means the fraction is never 0, which means we have no possible places where this changes concavity. So we just have to test a value to see what the concavity is here. So I'm going to substitute, since I can plug in anything after 1, I'm going to plug in 5 because we know that worked before. And we see that f double prime at 5 is 3 over 2 times 4 to the 3/2, which ends up being 3 over 16. The bottom line is it's a positive number. So that means that our function is always going to be concave up on its entire domain. Okay, so we can answer that question. It's concave up on the interval 1 to infinity. It's never concave down because we don't have any intervals there. And that means there's also no point of inflection. So that means this function is always concave up. It attains a minimum value at 10 comma f of 10. And we're increasing on one side, decreasing on the other. Let's take a look at what the graph looks like. And there it is. So just a couple things about it. So you notice the x-intercept at 34.971, just about 35. We have our minimum value at 10 comma negative 8. And naturally, f of x was x minus 6 square root x minus 1. So f of 10 is 10 minus 6 square root 9, which is 10 minus 6 times 3, which is 10 minus 18, which is negative 8. So that all works right there. Okay, so that verifies that result. Notice also, this is not an asymptote, but if I want to know what that point is right there, this is 1 comma f of 1. When you plug in 1, you get 1. Okay, and you notice that the tangent line is going vertical there, and that's reflected in where the derivative was undefined. Okay, so at least these aspects do make sense. And you notice that the graph is always concave up on its entire domain. So there is the graph of our function f of x.